What's up, guys? Welcome back to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry course video for you guys today. And before we get into today's video, please make sure to smash the subscribe button down below, hit that like button on this video, as well as hitting that bell to get notified on any of our channel's latest posts at eCoreAcademy. Alright, let's jump right into it. Today's lesson topic is all about styles of proofs, and it's about discovering what are the different kinds of proofs and what are their different properties. So this is a bit of a shorter lesson today. It's important that we cover the styles of proofs because proofs in general are very, very important, and we have to learn the basis, the fundamentals, their organic visual representations before we actually get into the meat and the entire content of what proofs really are in later lessons. But we will get into that in later lessons. But I will be breaking apart proofs more than I did reasoning, because proofs is very important in geometry, and that's what geometry basically revolves around, proofs and reasoning. Alright, let's jump right into it. So before we get into the different types and styles of proofs, we just have to know the basis definition of what a proof is. So proof, or a form of proof, is a clear logical structure of reasoning in which uses accepted ideas and logic to reach a conclusion. So it's very similar to reasoning, except that it uses reasoning for proof. So it takes these logical structures of reasoning, and what it does is it takes previously accepted ideas, just like reasoning does, and it can even use reasoning statements to actually prove a certain idea and to reach a conclusion for a certain problem. And just like reasoning statements that involve conditional complexes, proofs follow these same exact principles. You may also use postulates, theorems, principles, and previously proven deductive reasoning statements. So, like reasoning, proof basically takes a hypothesis and tries to correlate it with a conclusion. And in this case, proof is much more wide and ranged because it's about direct and specific scenarios and not general scenarios. So what you do is you take a form of reasoning statement that's already been proven before, and you can use that as proof for certain processes, for certain steps in a geometric process. And I'll get into what different steps of geometric processes are in these three different types of proofs, three most popular types of proofs. And like I said here, there's a form of using reasoning which is very general, but you can also use certain postulates, theorems, and principles, theorems, postulates, and principles being already proven concepts in the past, unlike newly made reasoning statements. And you can also use deductive reasoning statements as well. And in geometry, for every single circumstance or advancing in a computational process, you must have reasoning in order to present its validity. And reasoning being coming in the form of proof. So not just reasoning is a very real life term in this situation. What I'm trying to say here, you need to reason it. But in reasoning in geometry is not related to the reasoning that I'm showing here. Reasoning in real life is not like geometric reasoning, but it's like geometric proof. And that's what a lot of people get confused about. Proof is very different from geometric reasoning, but proof is very similar to real life reasoning. And you need to prove and back up every single step of the way that you take in any computational process. If you're trying to prove something and just in general, or if you're trying to clear up a situation or a problem. And the most common and accurate way to do so is by utilizing specific algebraic proofs in these three styles. And these are your algebraic proofs. They come in forms of postulates, theorems, and principles. And I'll recreate a whole entire new lesson about that because it's a very large lesson. So I'll probably break that down as well. But algebraic proofs are your main proofs that you're going to come across in geometry. All right, on to the first style of proof. So we have the two-column proof. The two-column proof has a column with all of the steps in a problem or geometric scenario / process. So this statement side, this basically represents the steps, the problem, the process, the scenario. This is where everything happens. This is the computation. Like, say, for example, you're doing x plus 5 equals 10. You're subtracting 5 from each side. It's a numeric values most of the time that you're going to be showing here, and this is a reasoning statement. So the second column will be the justification and reasoning behind each and every computational step, or each and every momentous step taken in the statement side. And the most common types of proofs are the two-column proofs, as shown here, and the paragraph proofs, which is going to be up next. So I'll just give you a little equational example just to show how this whole thing works, the two-column proof. If I give you the equation of 3x plus 10 equals 25, we're going to plug these numeric values in the statement side, the whole computation, how we're going to solve it, break it down each and every specific step, and then we're going to give a reason for each and every step that we take. So if we start with 3x plus 10 equals 25, if we put that right here in our statement side, what we're going to put for the reason side is what's given, because the given statement here for the reasoning is basically what's given as the problem. So that's the reasoning because it's the given problem. The next step that we're going to do is we're going to subtract 10 from each side because we're trying to isolate the variable. So what we do is we're going to subtract 10 from 3x plus 10 and subtract 10 from 25 so that we get 3x equals 15. And we're going to put that right here in our statement side. And then our reasoning for that second step would be the subtraction property of equality because we're trying to level out the equations. And since we're subtracting from one side, it's going to always subtract the same value from the other side to maintain equality. And then finally, what we're going to do is in order to find the value of x, we're going to have to isolate the variable entirely. And we're going to do 3x equals 15. We're going to divide each side by 3 in order to isolate x and give the value of x to equal 5. And the reasoning for that would be the division property of equality, since we're doing we have the same exact reasoning behind that. So those are the three reasoning statements for the three computational processes. All right, let's move on to the next type of style of proof. So the next style of proof is the paragraph proof. Just like the two-column proof, it's one of the most popular. The two most popular ones are the two-column proof and the paragraph proof. So the paragraph proof is a proof in the form of a paragraph with, as the title and the name of it suggests, and every sentence being a separate proof statement of a geometric process. So basically what you're doing here is instead of organizing into two columns or you're basically using bulleted form, it's not necessarily in sentence form. All you're doing here is just writing it out entirely. It's very simple. You're just writing out for every proof. So you're just saying in every sentence, because of this, this happens. So you're basically saying, like, say for example, if I give you a square here as an example, this is just a paragraph just to represent that. That's my proof. So if you're given a square here and you're trying to prove that this is a square, you already know that this is a square, but you're trying to prove it. So what you would do is you'd start off with your first sentence saying, you're going to start off general. You're saying that this figure is a square because it is a parallelogram. And then you would prove, and this is in sentence structure, so with periods and everything, and proper grammar and proper sentence structure. That's all it is. You're just listing it out word for word. And that's why this oftentimes does not beat the two-column proof, because the two-column proof is much more organized. And paragraph proofs normally use diagrams, then break it down through words, and the diagram would be the representation of a process that needed to be proved. So this is the problem and this is the solution. So if we take a square, we're trying to prove that it's a square, and we're given that it is a square, but we need to prove why. We can show that, oh, this figure is a square because it is a parallelogram. Then in the next sentence, we can say it is a parallelogram because it has two sides that are parallel sides, two pairs of parallel sides, and we can prove that with equations if we're given more variables or if we're given coordinates. And it's also a square, and it's a rectangle because it has four right angles or four perpendicular intersections. And finally, we can prove that that rectangle is a square because it has four equivalent sides. So that's how you'd prove it. You break it apart into sentences, and each sentence would either be building off of the last sentence or it would be its own separate statement. All right, and finally, we have our flowchart proofs. And a flowchart proof is not as popular as the other two, of course, because of how often it can get confused. But you will get later on, you will discover this in later topics, maybe Algebra 2 sometimes, and maybe even pre-calculus, because this is a very simplistic one. But you've also probably heard of these way back in elementary school, maybe in 4th or 5th grade when you were doing science projects or just science relations. So, flowchart proofs. A flowchart proof is a geometric reasoning proof that graphically represents a logical flow and shows statements and solutions with conclusions connected by arrows. So what it does here is it takes a very general problem here, as stated here, like these are three different problems here broken apart from a certain issue, and it basically breaks them down step by step into different reasoning statements all the way to a very specific conclusion. So And in a flowchart proof, you take a given scenario to prove and place it on top. You then make statements that are generic to prove the situation as you keep expanding. So what I mean by that is, in a flowchart proof, you basically take your situation, your problem, or your scenario, you put it to the leftmost side or the topmost side so that you can expand off of it and use your proof statements to basically dissect those problems and those original statements that you're trying to prove false or true. And what you do is you start from generic statements. Say, for example, with a parallelogram, you're trying to prove whether or not this figure is a parallelogram. So instead of these 3 squares, you'd have 1 square here, and it says this figure is a parallelogram. And then what you would do is afterwards you would expand it off into 1 and 2 sections. And what you would say is the first section would represent that, oh, it has 2 sets of parallel sides. And then the next box would say, oh, it has equivalent opposite angles as well as equivalent opposite sides. And you would keep expanding off of that in order to prove finally and restate your given statement by saying that yes, it is true, and yes, that the figure here represented ABCD is a parallelogram. Alright guys, that'll be it for today's lesson. Please make sure to like and subscribe down below on this video. Please visit our website link at eCoreAcademy.org. Visit all of our socials at Facebook, Twitter, Instagram, and email us at our Gmail at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. And our website is going to have full unlocked access to worksheets, integrated quizzes, as well as note sheets that go along with each and every video and are organized into different courses, and our different courses represented on YouTube. Alright guys, that'll be it for today's lesson. Hope you guys enjoyed, and I will see you in the next one. Peace.